Hello everyone, this is a review of the Physics 30 Alberta curriculum released item question from the Alberta website. This one's from the 2009 released items and it's question 24. It's a magnifying glass question. So it's asking at what distance above a page would a convex magnifying lens that had a focal length of 10 centimeters have to be held in order for the image that you see to appear upright and 3 times as tall. So hopefully we're all familiar with the magnifying lens or the magnifying glass. It's a pretty standard optical device to make things appear slightly bigger, and people use it often to sort of look at text on a page. So here's a little picture of a magnifying glass looking at that text on a page, and you can see quite clearly that it is indeed upright and slightly bigger. We're going to try and get one that's 3 times as big. Okay, so 2 strategies here. We're going to first of all look at ray diagrams, and of course highly recommend anytime you have a lens question, do a ray diagram. Gives you a good picture of what's going on. And we should also really be able to, I guess we could solve this question just with a ray diagram alone, or at least we'll be able to eliminate some of the answers. But then we're going to go ahead and do our algebra and make sure, just clarify that we have got the right answer with some straight up algebra. So let's just quickly review some of the different ray diagrams we can have. Okay, so I'm not going to draw them all, but we can take a quick look at this nice summary page. These are all the different types of ray diagrams you can get with a convex lens or a converging lens. So starting at the top, just really quickly, hopefully we can see we've got there's our converging lens. This is actually with parallel lines. We don't normally talk about this, but if you were looking at something very, very, very far away, you can effectively say they're parallel lines. That's going to give you an image here. We're not going to be too concerned with this one for now. This one here is where the the object is further away than twice the focal length, and that's going to give you this inverted image here, inverted real and smaller. If we keep coming closer to the lens, this is now twice the focal length away. This is going to give us our inverted image, and notice that the size is going to be the same. The size of the object and the size of the image, the same. This next one here is the object being somewhere between the 2f and the f, in other words, somewhere between twice the focal length and the actual focal length. This once again is going to give us an inverted image. In this case, it's going to be slightly bigger, but also real. Okay, so these first 4, 1, 2, 3, 4, these are all images that are produced by an object that is further away than the focal length. So past the focal length, past the focal length, past the focal length. And these all give us inverted images. Now we're getting onto an image now that's actually on the focal length. And this is going to give us, well, actually, it's not even going to give us an image. It's going to give us these 2 parallel lines. So no difference here. These lines are just not diverging. It's going to take a lens in your eye to produce the actual image. So it's really this last one that we're interested in. This is the one that's going to produce the circumstances for our question. So this is when the object is between the focal length and the lens. If you put the object between the focal length and the lens, these 2 rays diverge away from each other, and we become interested in the virtual image. These dashed lines that come backwards on the same side of the lens as the object, and now we produce a virtual image over here that's magnified and upright. And that's the condition that we need to be in for our question. We need it to be upright and 3 times as tall. Okay, so we know that the focal length has to be 10, and we know that the position of the object, or the distance the magnifying glass is away from the page, has to be less than this, has to be within the focal length. So what we're going to do is just play around with a couple of different arrangements, and we should be able to eliminate some of our keys. or some of our potential answers. We've already eliminated a couple because we've established that the object has to be placed within inside the focal length, so it has to be less than this 10 centimeters. So it can't possibly be, it can't be C. Our answer cannot be C. I'm going to cross that out. And it cannot be D. Okay, so it's going to be either A or B. So let's play around with a few ray diagrams, and we should be able to just qualitatively eliminate one of these answers and thereby get the correct one. So let's go ahead and put our object about halfway between the focal length and the lens. So that's going to look something like this. Okay, it's going to be virtual. It's going to be virtual. It's going to be upright. It's going to be larger. And if we take a bit of a qualitative look, really without getting my ruler out, I can kind of tell that that's about twice as big. So I'm saying my magnification is times 2. And that's obviously not enough because we need it to be 3 times as tall. So let's move this around. I'm just going to pick arbitrarily. Let's bring our object in a bit closer. Let's put our object even closer to the lens. So now we have our object about, I don't know, what is that? A quarter of the way towards the lens. And I'm not even using a ruler here, I'm just sort of guessing. And if I do that and I trace my ray diagrams, here I get my virtual, upright, larger image, but it's about 1.3 times as big. So clearly, by going from the middle closer to the lens, I'm actually making the magnification smaller. So hopefully you can see that this is not going to be the case. And so right away I can actually go ahead and just cancel out one of these answers. It can't be 3.3. It can't be 3.3. So I'm pretty confident I've got my answer already and I haven't even done any algebra. It's probably going to be B. But let's go ahead and do the algebra, and we'll also check with another ray diagram quickly just to confirm that we've understood this correctly. So I'm going to, again, just arbitrarily move my object from the middle further away now from the lens, and hopefully that just confirms what we've just said. Okay, so here it is. There's my object. It's been moved back slightly from the center of the focal length and the lens, and now hopefully you can see that it's making an even bigger image, and I'm just sort of guesstimating here that that's about 3 times as tall. So it's 3 times as tall, it's upright, it's virtual, 3 times as tall, it's upright, it's virtual, and if you note that it's about 3/4 of the way back from the lens, in other words, 3/4 of this 10 centimeters, so it's very likely to be B. So now we're going to prove to ourselves, we're using algebra, that it really is B as an answer. And of course we can use our magnification equation. So we've got magnification is going to be equal to HI over HO, hi-ho, and also to negative DI over DO. Of course, we also have our lens maker's formula, 1 over F, 1 over DO plus 1 over DI. And essentially what we're going to do here is combine these two equations. So let's take a look at this one first of all. This one, magnification one. So magnification is 3. I'm not really interested in the height of the image or the height of the object. I'm only going to be interested in the DI and the DO. So I'm saying that 3 is equal to negative DI over DO. And that, of course, means that I can say 3DO is equal to negative DI. Okay, and then I'm just going to move this negative sign over. So I'm going to say that negative 3DO is equal to DI. And this means that I can now substitute this, this statement in to this part of my equation. So now let's take a look at our lens maker's equation. And just before we go ahead and do this, we should be by now pretty comfortable with adding and subtracting fractions. So just to recap really quickly, if we have A over B plus C over D, we're going to go ahead and do our little cross multiplication. So we're going to say, what the aim here is to combine these two fractions together into one. So to do that, we're going to cross multiply A and D together. So we'll go ahead and do that down here. So A, D, so A times D. And then we're going to cross multiply B and C. We're going to keep the plus sign in there, so plus BC. And now we can multiply out the bottom part of the fraction. So that's all over, this is where it's combined into one, all over BD. So that should be a little bit of a refresher. This is kind of a key skill here in any lens equations, because you've got this fraction, adding of fractions going on. So let's combine now. We're going to bring our negative 3 do, we're going to bring that over and substitute it for this di. And of course what we're trying to do is solve for do. Okay, we're trying to get our do. So we're going to start putting some stuff into this equation. First of all, I know the focal length, so I'm going to say 1 over 10. And then I'm going to go 1 over do, okay, plus 1 over negative 3 do. Okay, now I have to go ahead and just add this fraction together. So let's go ahead and simplify this. 1 over 10 is equal to, well, now I do my cross multiplication. So 1 times negative 3 do is negative 3 do, plus 1 times do is do, and then all over do multiplied by negative 3 do. Well, this is essentially 1 do multiplied by negative 3 do. So I'm going to have a negative 3 do squared. Okay, we can simplify this a little bit further and get down to our solution pretty quickly here. Hopefully you can see negative 3 do plus do is going to give me a negative 2 do. And then I'm going to go over negative 3 do, and that is still, of course, equal to 1 over 10. Then I'm just going to come over here for some more space. I'm going to get rid of the negative signs. They can just kind of cancel out. Oops, I forgot the squared. Negative 3 do squared. I can now cancel out this do with the squared, which gives me 1 over 10 is equal to 2/3 of do. Okay, and now we can just simplify this by doing a reciprocal of both of these, or putting them both to the power negative 1, and that's going to give me 10 is equal to 3 over 2, and my do can come up to the top. And now hopefully you can see that if I divide my 10 by 3 over 2, I'm going to get do to be equal to 6.66 recurring. And there we have it. That's our key. That's my answer. Confirmed. I know that I'm right.